Hello, welcome. Today, let's solve the Leetcode problem 851, loud and rinse. Let me explain the problem a little bit because some of people don't like this problem because they don't understand it. So actually, it is a very good question, and it is a very good question to practice topological sort. If you can use DFS, you can still solve it, but that is not so easy. If you use a topological sort, you can solve it easily if you understand the logic. Now let's understand the loud first. The loud and rates. So this is just means there are two things. So one is rates, another one is quiet. So we have the rates. So let me explain the rates. So for the rates, it's basically inside the rates array. Inside there will be some values with A and B. For example, this is A and this is B. So for rates I, for the AI and BI indicate that AI has more money than BI. So it means for the it has more money than not 1 has more money than not 0. Not 2 has more money than not 1. And now let's check the return. Because here is just to understand the situations. It means x is richer than y and y is richer than x at the same time. That will be not possible. It only be either x is richer than y or y is richer than x. So you basically need to understand that. Now let's talk about the result. So we need to return an integer array answer where answer x equal to y. So if y is the least quiet person, so we need to, it is quite confusing if you read the question again and again. So that is why you need to analyze the problem, check the examples, maybe you understand. So for the answers x equal to y, so y is the least quiet person. So actually y is a not. It is not the quiet value inside the quiet array. It is a not. And it is with not. It is the least quiet person. It means this node, this person has the least quiet. Now let me explain it in whiteboard. You may understand that clear. And I will analyze the time complexity later, but I will first talk about my ideas for this topological sort problem in the whiteboard. Let me check the whiteboard. I prepared some drawings for easy understanding the topological sort. Basically, what we need to return? We need to return a person. For example, for the first person that is not 0. What we need to return? We need to return all the persons that is richer than this 0, and also we need to return the least quiet value. What do I mean? So for example, this 0 is here. So 1 is richer than 0. Why I make a drawing like this? Because according to the problem, I needed to make some drawings like the topological sort structure. This one just means 1 is richer than 0, 3 is richer than 1, and 5 is richer than 3. So according to the answers, I can configure a structure like this. But what we need to return? We need to return the least quiet value. So which one is the least quiet? So for here, for the not 5, the quiet value is 1. Why it is 1? Because we have a quiet array. Inside of the quiet array, for the index 5, this is for not 5, so the value is 1. So this is just to put the values near the node, just to make it easier to analyze the problem. So for the 0 position, basically we need to return a not 5, but not the quiet value. We need to return the node because we need to return the person according to the problem. So for this one, if it is 0, what are we going to return? We're going to return this not 5. And for the not 1, it also means person 1. So this is by the way, this is just a result array. So this is just for my result, what I'm going to return. So for the person 1, it's also the same because this quiet value of 1 is the least quiet. Yeah, and this 5 is the person, so I'm gonna return a person with 5. What about not 2? So for the not 2 also means person 2. There's no person that is even more quiet than this not 2, so it will gonna return itself, so it will be 2. And for 3, similarly, it's the same. We're gonna return a 5. So 4, 5, 6, and 7, you can say 4, 5, 6, and 7. So let me first check 4, 5, and 6. So for 4, 5, and 6, there's no node that is even richer than itself. So we just need to return itself, 4, 5, and 6. Now let's check the 7. For the 7, the quiet value is 0 because at index 7, it is the quiet value is 0. So there's no person has a quiet value than this than this person 7 because there's no quiet value even less than the 0. So we just need to return the person itself. We just need to return this 7. So actually, this is the final result for our first example. Yeah. But how should we get this result for the code? Yeah. So this is why we're gonna use the topological sort plus BFS. It makes the situation much easier. First of all, we're gonna prepare two variables. So one is the graph. So the graph is like this structure. It is easy to prepare. Yeah, because we just need to prepare a dictionary, and the value will be list, and k will be the node. And according to this structure, you just need to check the edges inside the richer array. Normally, you can get this kind of a structure for the graph. And at the same time, you need also to prepare an in-degree array. So for the in-degree array, basically, in-degree, this means in-degree array inside, you need to prepare all the integers of the node. So there are 7 nodes. In total, there are 8 nodes. So for each of the node, you should prepare the integers. So for example, for the node 0, so the integer is 1. For the node 2, there's no integers, so it is 0. Yeah, so this is also easier. While you are preparing the graph, you can also prepare the integers. Yeah, because this integers is will be used for later on for the BFS. Yeah. Now, after that, you just need to put the values of the integer with 0 inside the queue, and you can use the BFS for the queue. Yeah, let me explain why we can update the values. So for this problem, even for updating the values, it is difficult because it is more confusing. There is a quiet array, it means the quiet of each person, and there is also the node, which means each of the person. Yeah. Now, how should we update it? Now, let's first check the node 2 for this node. Do we need to check node 5, 4, or 6? We don't need to check because we cannot find a person that is even more quiet than 6 or 5 or 4 because there's no node connected to the 6 directly. Yeah, I mean the arrow connected, not others. There's no node connected to 6 or 5 or 4. Only 6 connected to 3. Yeah, but there's no node connected to 6 directly. So we're gonna not analyze 4, 5, and 6. So that is why for 4, 5, and 6, for this it will be itself. It will be just yeah, the least quiet person will be itself 4, 5, and 6. Now we are going to check the node 2. So for node 2, it's also the same. You cannot find a person that is even richer than this node 2, than the person 2. So for the node 2, it will also be itself. It will be 2. Yeah, as you can see here, it's gonna be 2. Here will be 4, 5, and 6. Yeah. Now let's check another one. Let's check a difficult one. Let's check the person 1. Yeah, how should we update this one? Normally, we can see that. So normally we already put this inside the queue. Yeah, if we pop it out from the queue, it means we got a person of this 2. Yeah, we got a person of 2 and its quiet value is 5. And here we have a person 1 and its quiet value is 2. Yeah, as you can see, the quiet value for this person 1, the quiet value of person 1 is less than quiet value of person 2. It means we don't need to update. Why? Because we need to find a smaller required value, because this 5 is bigger. We don't need to do that. Yeah. Now let's go back to another bronze. So for this 3. Yeah. But for our function, this for the q, we've already pop out this node 2. After that, we're gonna append this node 1 inside our queue. Yeah, but for the queue, the next node will be 4, 5, or 6. Yeah, this is just according to the structure of the BFS. Yeah, because it's not a DFS, it's just a BFS. So 2 finished its work. We didn't update the value at node 1. But let's check another one. Let's check the 4. So for this node 4, for this person 4, so its required value is 6. It is even bigger, so we don't need to update. But for here, we need to update with the node 3, so we don't need. And here, this is important. This required value for the node 5 is 1. And required value for the node 3 is 4. 1 is less than 4, so it means from here, we need to update it. So for the index 3 of the result, it will be updated to what? It will be updated to 5, because this is the node. So this is required value. 1 is smaller, so it will be updated to 5. So for here, before, when I preparing my result array, it will be just 0, 1, 2, 3, 4, 5, and 7. Now for this 3, it will be updated to 5, because node 5 is even more quiet than this node 3. Yeah, but how should we update it? So basically, we're gonna check like this. So this q means the quiet variable, and this r means my result array. So if the q result 3, so 3 is the node, this person is less than q, you can check here. If it is less than q with r4, yeah, because in the required value, it is 4 is less than 6. We don't need to do anything. Yeah. But what if the QR5 is less than QR3? It means this person, is less than this 3. So we need to update it. So how should we update the value? We just need to update the result array. So the result with the person 3 needed to update it to a smaller value. It's going to be equal to the result 5. So result 5, what is the result 5? It is 5. Yeah, because this is when we are preparing the result array. So we're going to preparing it like 0 to 7. So 5 here. So result 3 will be equal to result 5. It will be equal to 5. So this is why from the person 3, it will be updated to 5. Yeah, it is confusing, but after you analyze, make the drawing, you analyze the array, it will be like this. It cannot be directly to this 5. It has to be result 5, because inside the result array, it will be store the quiet, the least, the most quiet value. Yeah. No, let's, if you don't believe it, if you don't believe this result 3 will be directly equal to 5, it's gonna be wrong. It have to be result 5. Yeah, if you don't believe it, let's check the next value 1. So for the result 1, if it were to update it, how should it update? It should be equal to result 3. Why? Because for this one, the quiet value for the node 1, it is 2. But for the quiet value for the node 3, it's not 4 anymore, because it has already updated with 1. Because for the node 3, for the result 3, it has already become 5. Yeah. So for the result 5, let's for the quiet 5, let's check. Yeah, for the quiet 5, it has already become 1. Yeah. So this is why the result 1 should be equal to result 3 and should equal to 5. Yeah. And now you can check result 1, so the value is 5. Yeah, if you don't believe it, let's just check why I'm going to check it like this. So this is the quiet. So the quiet are quiet. Let's check quiet with R1. Yeah, so this is a quiet R1 is more than this quiet R3. Yeah, so this is actually the most important things we need to take care. So for the quiet R1, so what is the value? So the value is 2. So this is the quiet value. It is 2. So what about the quiet R3? So for R3, it has already been updated to 5. You can see here, it has already been updated to 5. What is Q5? Q5 is 1. So this value is 1. It means we find an even more quiet value. This QR3 is even more quiet. This is 1. So what we need to do, we just need to update the value. So the result 1 should be equal to result 3. Actually, it is here. So the result 3 is 5. So result 1 is updated to 5. Yeah. Now let's check the next one for 0. For 0, I don't need to check all the formulas, but for 0, we just need to compare with this person 1. So for the 1, the quiet value has become 1, not 2 anymore. So this quiet value is 3. So 1 is smaller than 3. So for this quiet value, it will be updated to quiet value 1. But for the person, it is not 5. So this is why for the not 0, it's still 5. Yeah. Now let's check the last one for the not 7. So for the not 7, the quiet value is 0. 0 has already been the smallest quiet. The quiet value has already been the smallest. We don't need to compare with this. Yeah, if we need to compare only with this one, so the quiet value is 1 for the not 3, but for not 7, it is 0, so we don't need to update. Yeah. Now let me go to the code. Yeah, and normally when you connect this drawing and the analyze of the formula, then with my code, normally you can understand why I'm gonna do it like this. Yeah, basically let's prepare some template code for the topological sort. So I'm gonna use the BFS. So this is why I'm gonna use a graph, and I'm gonna use int degree. So the graph will be Z and int degree will be an array. So it will be default dict, and inside it will be a list. And this int degree will be an array. I will be initialized at 0 times the length of the quiet, because the quiet is how many nodes, how many person do I have. Now I'm going to loop through the richer array. So this means A is always richer than B. So from here, we know AI has more money than BI. And we're gonna prepare our graph like this, ga.append according to my drawing B. And for the int degree, we need also to update to B, because A pointed to B for the directions. So the int degree of B should plus 1 plus equal 1. So for here, we've already prepared the variables for the graph and the int degree. Now we just need to prepare a queue should equal to the queue. This is also basically the template code. We just need to put the node inside. So for I v in enumerate degree in degrees. In degree, if this v, if the value equal to 0, we just need to put the node inside the queue. Now I'm going to prepare a result. As I explained earlier, so the result will be the list of range n. It is just gonna start from 0 to n minus 1. Yeah, because if we don't need to update it, so it will be the value itself. For example, result 0 should be 0, result 1 should be 1. So for example, result 7 is 7 because it has already been the most quiet person. Yeah, for this 4, 5, and 6, it will be itself because we cannot find a richer person that is even more richer than 4 or 5 or 6. So this is why we're going to prepare the result like this. Now I'm just going to use BFS. So for the BFS, just need to check the queue. Now my node will be pop out from the queue dot pop left. Now I'm going to loop through the neighbors. So for neighbor in Z node, yeah, I'm going to check one by one. So if let's check the quiet value. If quiet with result, now we are going to check this node with this neighbor. Now let me go back to the drawing. So what is a node? What is a neighbor? So for example, this 2 is a node, and this 1 is neighbor. So this 5, for example, this 5 is a node, and this 3 is its neighbors. So which value should be the smaller? Yeah. So if the node, the quiet value of the node is smaller, we're gonna update it. Yeah. So if the quiet result with node is smaller than the quiet result with neighbor, so when we update it, we should update the neighbors but not the node. So the result neighbor should equal to result with this node, because inside the result node it is just the least quiet value, but this result node is the person with the least quiet value. So this is the most important code actually, and except that it will be the template. Now I'm just need to finish the template code for the BFS plus topological sort. So for the in degrees, it will be update. In degrees will be updated to, for the neighbor, it will be -1. Yeah, so this means if I've already finished the traversal of 2 to 1, basically I've already put 1 inside my queue, and this end will be disconnected. Yeah, because for the next one, I'm not going, if it loops through the 1, I'm not going to check this one anymore, so the degree would be equal to -1. Only after -1 or some areas -1, if it finishes 4, 5, and 6, so there will be no node. In degrees for the node 3, there will be 0. Now it will be put it inside the queue. So this is why I'm going to update the in degree. Now I'm going to check it. So if in degree this neighbor equal to 0, I'm going to put it inside the queue dot append with this neighbor. Yeah. After that, I'm going to return the result. So because this is what I prepared for return, and inside it will be updated according to the person with the most quiet person. Yeah, I just wanted to update the richer person and also the most quiet person. And according to this design of the topological structure, it's gonna solve this problem, because 6 is always richer than 0, 5 is always richer than 0, and then we just need to check the values of 5 if it is less than 0. So 1 is less than 3, so we're gonna update it. But while updating, it will be updated it like this with a quiet result with the node. Yeah, so this is gonna be a little bit difficult to find this formula. Now I finished all my code. Let's just run it to check if it works. So for AB in reader, now, yeah, I forget a in. Now let me run again. So this n, yeah, I didn't prepare the variable n. I'm gonna use quiet. I'm gonna use the length of quiet. So this n basically is the length of the quiet array. Yeah, now you can see it works. Now let me submit it. After that, I will analyze the time complexity and why we have to use the topological sort with BFS or DFS, because this one really saves the time. You don't need to check the node one by one. You just need to use just like one loop. So this loop for the time complexity is n. N is the number of nodes. And for here, this time complexity is just m. So m is the number of edges. Yeah, as you can see, it's pretty fast. It's nearly 87% of all Python 3 submissions. Now let's check the values of this m or n. As we know that there are only 500 vertices and how many edges? So there are n times n. Basically, this is n times n. So the time complexity is n times n plus this n. So finally, it will be n squared. So 500 times 500 is not a big value. That is why it is so fast. Thank you for watching. See you next time.